back. So today we're going to be doing functional equations. So a lot of you might find this statement extremely scary, and then if you see this in a test you don't even try it because it looks very difficult and intimidating. But today we'll go through the process of how to solve functional equations, because they're very easy to get a lot of points on and they do appear quite often. Okay, so first of all, we have to know what this means. What does the question actually mean? So, you're given some function f that has domain real numbers, codomain real numbers, and this property has to be true for all x and y and reals. You know that symbol, right?
What is it? Does it mean it has to be true?
For all. So this is for all. That means the same as that, and that means there exists. If you see those symbols appearing, that's what they mean. Okay. So, no matter which values of x and y you choose, whether they're any real numbers, this must be true. So, the idea to this is find the rule that you apply onto x and y to always get this relationship out. Okay. So, the first step for every functional equation question in existence is you try to guess a solution. Does anybody have any ideas for solutions?
I mean, isn't it easier to just try some values and see what comes out? Because I wouldn't know where to start to guess one.
Okay, so that would be the next step after this, but this is kind of a way of checking yourself. So you start off by perhaps noticing that f of x is equal to x squared always satisfies this equation. So this is always the first step. You try to guess solutions, normally for like a minute or two. You always, mostly find one solution of some form like that, and maybe if you stare a bit longer you'll get another solution popping out. So the reason that this is useful is that suppose you're trying to find certain values and plug in other values, then you can know what to expect. So in this case, with f of x,
What leads you to that?
what? This.
No.
So
I would have said x equals y, and then that kind of comes out.
okay, well, you can look at the way that this is structured, and if you have a good sense of algebraic identities, you'll see that something x minus 2xy plus something y is very similar to x squared minus 2xy plus y squared. And you check it on that side, or it's the same thing. Okay, so this gives you one solution that could work. It might not be all of them, maybe it is the only one. You still have to prove that it is. So a rule of thumb for functions that you can try is stuff like check does f of x equal x work. In this case, no, it does not. You can try does f of x equal 0 work. No, it does not. You can try f of x equals x squared, which does work in this case. You can try f of x is some constant times x. So that sometimes appears. Another one that sometimes appears is f of x is x plus c. So you could have a constant that could cancel it out. Anyway, so the reason that this is helpful is that it helps you to plan out your approach to solving this functional. So in the case f of x equals x squared being a solution, you know that you shouldn't be looking for stuff like a value of a such that f of a is equal to -1. So since that is a solution, you can't expect that to appear without explicitly going into a case where that would be valid.
Would we maybe looking at polynomials? Or
No, any function whatsoever.
whatever x root x?
Yeah, it could be whatever you want. I think I've seen one that was let f of n be the nth approximation of pi using this specific method of representing pi. And where did that come from? But it just magically works. Okay, so like I said, that's only one possible solution. We have to find every single possible solution that could work. Okay. So, even through checking, you might not get all solutions because there's pathological solutions, like the one I mentioned earlier, that you wouldn't be able to guess if you stared at it for 1,000 years. Okay? So, then the next step is we start playing around with the expression. So, we're told that no matter which values of x and y, that relationship must be true over there. So in particular, you can say, let's let x be equal to 0 and y be equal to 0. So what do you get in that case? Okay, so you get f of 0 is 2, 0 minus 0. And you can simplify that to get that f of 0 has to be equal to 0. Okay, so what that tells you is that for every possible solution to the functional, it must be true that f of 0 is 0. Okay, that sometimes that's useful, sometimes it's not. In this case, it is. Okay. Do you have any other ideas for values you want to try?
X and x, 1 and 0.
Okay. Let's try 1 and 0 first. So consider x equals 1 and y is equal to 0. Okay. So what do you get when you plug that in? Okay, so you get f of 1 equals f of 1 plus f of 0 minus 0, which you simplify to get that f of 0 is 0, which, like we said, is something we knew already. So that doesn't help. Okay. The next thing, yes? Okay.
And then y equals x?
Okay, we'll get there in a second. So another idea that could be useful is you let one value change and the other one just stays as a constant value, which gives you, or it constrains the equation a lot more because you only have to worry about the one variable, and sometimes you can get behavior out of that. So if you consider x being some k and y being fixed to 0, then you get f of k equals f of k plus f of 0 minus 0, which is not useful in this case because it just gives us f of 0 is equal to 0 once again. Okay, so that wasn't useful. So next up, we saw that fixing one value and letting the other one change to whatever you want isn't helpful, and fixing both of them doesn't seem that helpful. It only gets you specific values. So maybe you think, okay, let's let both of them vary, but so that we can keep some control, we'll let them be the same thing. So consider x being equal to some y being equal to some k. Okay. So what does that give you? working on. You there? Yes.
Sorry?
What is it?
Yeah, she said it'll be fk minus k, which is 0. And then you would have fk, or 2fk, rather, minus 2k squared.
Okay, this is true. So we get that f of 0 is 2 f of k minus 2k squared. And okay, this is 0. And this is, you can divide by 2 to get that. At which point you can rearrange it to get that f of k must be equal to k squared. And since we didn't pick a specific value for k when we made the substitution over there, this means that this must be true for all possible values of k that we can substitute in. Okay, so we've proven that if a solution exists to the function, it must be f of k is equal to k squared. But that doesn't necessarily mean that there is a solution. Yeah. So this is probably one of the most important things about functional equations, is you have to check. So you could go through pages and pages of working out and show that f of x has to be x cubed plus 7x squared minus a sine of 3x, whatever, and be very happy with that and move on. But that doesn't mean that just by plugging in stuff you can't get that that function necessarily satisfies the original equation. So just because you derive that f of k equals k squared doesn't imply that f of k equals k squared is a solution to the original equation. Is that? So if you want to see it symbolically, you're taking...
Well, it is when x equals 1.
No, so...
because that was the condition for f of k to be k squared.
Yeah, but... So we derive that f of k equals k squared from that. But what we're doing is we're taking some expression and then saying that that expression implies a second statement, and then that implies a third statement, which implies a fourth statement. But A implies B implies C implies D doesn't mean that D implies A. So that's the logic here. So the way that you do this is you... Sorry. Yeah. So you take your possible solutions, you list all of them down. In this case, it's only f of k equals k squared. You say if f of x is equal to x squared for all x elements of the reals, then the left-hand side is equal to f of x minus y, which we're saying is x minus y squared, which is x squared minus 2xy plus y squared. And then separately, we say the right-hand side is f of x plus f of y minus 2xy, which, using what we're assuming the function is, gives x squared plus y squared minus 2xy. And from here, you say that the left-hand side is equal to the right-hand side for all values of x, the real numbers, and this completes the check. So if you don't include this step, this check, you will get at most 6 out of 7 for the question. You have to check every time. So even if you don't fully solve a functional, it's often useful to list f of x equals x satisfies it, f of x equals minus x satisfies it, f of x equals 0 satisfies it, and that could sometimes be worth a few marks. But if you don't check it, they might not be convenient. Okay, so that's that functional, and that process that we did of just plugging in values, seeing what you get, plugging in more values, seeing what you get, using stuff that you found previously, that's how you do every single functional equation question. Which is why it's useful to practice them, because they're all exactly the same. Okay.
So have we established that there are definitely no other solutions?
Yeah. So we proved that if a solution exists, it must be f of k equals k squared.
Oh, I see.
And then, so if it exists, it must be that. And we show that that
Then it
actually
shows
works.
it exists.
Yeah.
But okay, so that f of k equals k squared, you got by saying x equals y, or x equals y equals k.
Yeah.
So x and y are being restricted to being the same.
Yep.
So what if they're not the same?
Well, you probably won't get much useful out of this equation. So that kind of shows why the check is necessary. Because you applied that constraint on your inputs and showed that the only consistent output is for f of x to be x squared. So you have to show then that that constraint didn't like make the thing false all of a sudden. So
Yeah, look, I mean, I understand the argument. So if x equals y, then you get f of k equals k squared. It's a possible solution if there exists a solution. So you've shown that a solution exists. So therefore, a solution is f of x equals x squared. But I don't know. I mean, I'll take your word for it, but I don't see quite how we've at what stage we have said that can be the only solution.
okay, so we go back here. So for all values of f, all solutions to that functional, you can set x to be y to be some value k, right? So for all possible functions that satisfy the equation, this f of 0 equals 2 f of k minus 2k squared must hold. Okay, and then from here we show that for all possible functions that can satisfy it, this must be true. So for all possible functions that satisfy it, f of k must be k squared.
You get examples where you get two solutions which are quite different. Like,
Yes.
So for example, you get examples where one might be a quadratic and one might be square root or
Yeah, you can get cases like that. So in the next, well, in one of those two, you can find examples. I think it's the first one which we can try. So, okay. So next up. So for functional equations, there isn't really a lot of theory involved, because it is just plugging in values and seeing what you get. But a few important terms that you should know is that f is called injective. If f of a equals f of b only when A equals B. And some set x, y with A and B equivalent x. And f is called surjective if there exists a Yes?
What does x and y mean?
So those are, x is the domain and y is the codomain of some function f. So it says f is injective if f of a equals f of b only when a equals b. So a way of understanding that is that you can't put in two values as input and get the same value out as output. Okay? And f is called surjective if there exists a value a such that f of a equals b for every b in the codomain. Okay? So an example of an injective function would be f of x is x plus 2. Okay. So suppose that there exists some a and b such that f of a and f of b are the same thing. Then that implies that a plus 2 must be equal to b plus 2, which implies that a must be equal to b. Okay? So that says that you can't choose two different values a and b and get f of a equal to f of b. Okay? Similarly, you can. This is also a surjective function, but let's use f of x equals x cubed as an example. So if you want f of a to be equal to some value b, then you need a cubed must be b. So a equals the cube root of b is a solution. And since the cube root of b is in the domain for every value of b that you choose, this is a surjective function. Okay. And a function is called bijective if it satisfies both of these two things. So injectivity comes up a lot more often than surjectivity, and it's useful because if you have a function or expression form, for instance, f of x is equal to f of 3x plus 2, and you have that f is injective, then that means since if you let, or if f is injective, then f of a equals f of b only when a equals b. So in this case, you can almost drop an f from both sides by letting a equal f of x and b being f of 3x plus 2. And from the condition of injectivity, you would get that f of x would be f of 3x plus 2. And from there, you can do the same step again to get that f of x must be equal to 3x plus 2. So just knowing that a function is injective through some process and having this condition is enough to satisfy or find all possible functions that it could be. Okay? So there's a special type of function which is called Cauchy function. So this is a function form that comes up quite a lot, and if you can reduce a function to something that looks like a Cauchy function, then you can just say, because all Cauchy functions are of this form, this function must also have these specific solutions. So it says is if you have f of x plus y being f of x plus f of y, then f of x is c times x is a solution if f is from the rationals to the rationals, or from the naturals to the naturals, or from integers to integers, anything like that. So anything except for reals, you can always say that f of x is equal to cx. Does anyone want to try and prove that? Okay, so the first step would be, okay, well, you can guess some solutions, and you would see that f of x equals x always satisfies it, x squared does not, 2x still satisfies it, 3x still satisfies it, minus x even satisfies it, f of x equals 0 satisfies it, so you guess that that could be the solution. So in that case, since f could be x times any real value c, there's no point trying to say something like f of 0 is equal to 0. Well, that is true. Saying something like f of 1 is equal to 1. That isn't always in the solutions. Okay? So you would start by saying, okay, let x equal y equals 0, and you get f of 0 is 2f of 0, which implies that f of 0 must be equal to 0. Okay, so that's one step, one value. Then you say, well, what happens if you let, okay, so this was x equals y equals 0. If you let x equal 1 and y equals 0, you get, well, that means f of 1 is f of 1 plus f of 0, well, but that's just f of 1, so this doesn't seem helpful. Okay, then you decide randomly to keep going. So what happens if you let x equal 2 and y equal 0? Well, you get that f of 2 is going to be f of 2 plus f of 0. Okay, well, that also doesn't really help. But what if you say, well, let x equal 1 and y equal 1? Then you still get f of 2 over here, but you get f of 1 plus f of 1 over here, which is equal to 2 times f of 1. Which says that no matter what value of, well, no matter what the function is, f of 2 is going to be 2 times whatever f of 1 is. Okay? So that seems slightly useful. Now you might think of saying, well, what happens if you let x equals k, where k is some value in the rationals or the naturals, including 0, or the integers?
So Robert, that's basically a difference equation, and you're saying the next one is a multiple of the previous ones, but an exponential.
So it looks like it here that f of 2 is some constant times f of 1, but it turns out that you should see this rather as f of 1 plus f of 1 and not 2 times f of 1, which you'll see in the next substitution. So if you let x equal some k, where k is in the domain, and you let y equal 1, then you get that f of k plus 1 is f of k plus f of 1, no matter which values of k you choose. So this seems slightly more useful, because if you know what f of 1 is, you can get every other value. For instance, let's say that f of 1 is equal to c, where c is some constant. Then f of 2 is f of 1 plus 1, which is f of 1 plus f of 1, which is 2 times c. And then f of 3 is f of 2 plus 1, which is f of 2 plus f of 1. So that's 2c plus c, so you get 3c. And then you can keep going with induction to get that f of 4 is 4 times c, where c is some value. And in general, you get that f of n is n times c, where c is some value that is the same as f of 1. Okay, so at this point we've only proven it for the naturals, including 0, but so this isn't true for all rationals. We've only dealt with whole numbers. You can extend this to the negative numbers by noticing that you can let, instead of x equals k, you can say let x equal k minus 1 and y equal to 1. So you'd get f of k is f of k minus 1 plus f of 1, in which case f of k minus 1 would be f of k minus f of 1, which means that you can say if you have f of 0, then f of minus 1 is f of 0 minus 1, which is f of 0 minus f of 1, which is 0 minus c, so you get a minus c over there. And then you keep going until infinity, and you'll see that this is still true for negative numbers. Okay, for rationals you have to do a bit more. You do induction on integers first, and then you do induction on numbers of the form 1 over a, 2 over a, 3 over a, etc., where a is some integer, not 0. And from there, it's not too bad to show that indeed f of x equals cx is the only solution for those possible domains and codomains. So the reals are special. They aren't included there because you can't do induction with real numbers, which is what we use to prove this. So, but if you look at this, it does still seem to work for real numbers, but that doesn't constitute the proof. There could be other solutions that you might not be able to find with this method. So it turns out that there are other solutions, which are all very crazy, and I can't find them online because they're so awful. So there are some conditions that you can put on f to make it a bit nicer. So if one of the following is true, f is monotonic. F is continuous. F is bounded on some if you have one of these four conditions is true, then it turns out that f of x equals c times x is the only solution. But don't worry too much about what these two mean. That won't come up ever, and it is a pain to prove that, so it probably won't come up at all. But f being monotonic is something that you should know. So this means that f is either strictly increasing or strictly decreasing. So that just means that if, for instance, with strictly increasing, if A is bigger than B, then you know that f of A is bigger than f of B, which is sometimes not too difficult to prove. And strictly decreasing, you just swap those two. That would be just like that. Okay? So yeah, so that's useful to know. So you can use this to turn certain equations into the Cauchy function form, and then be able to solve those, even though they may seem quite hard at first. For instance, again, don't worry too much about what continuous means. It's just for the sake of this question, I'm putting it there. Okay, so first step of a functional equation. What do you do?
Yes.
Can you see anything that could work? Nothing? Does f of x equal x work?
No.
Okay. So f of x equals x does not work. Does f of x equals x squared work?
No.
Okay. And
F of x equals 0.
okay. So f of x equals 0 is a solution, except in this interval 0 isn't included. So we kind of do.
So f of x equals 1.
Yeah, sure. So this is a solution. F of x equals 1 does satisfy that. Any other things that you may see? So So 2 to the x plus y would be the left-hand side. The right-hand side is 2 to the x times 2 to the y, which is 2 to the x plus y. So they're the same thing. Okay, so y stop there. Does f of x equals 3 to the x work?
Yes.
And f of x is 4 to the x? 5?
Yes.
6?
Yes.
Okay, you get the idea. So we conjecture that this is the general solution. Maybe it's not, maybe it is. We have to prove that. Okay. So for the first step, I don't know how many of you have seen this before, but so you all know how to take one number and raise it to the power of another number. So like 2 to the 5 equals that. You can solve that, right? Yeah, so that's 32. And if I said 2 to the something is equal to 32, would you know how to find that?
So log base 2 of 32.
Yeah. So there's this function called the logarithm. Which is defined by the logarithm of a is equal to b if 10 to the power of b is equal to a. Okay? So the logarithm log of 100 would be 2 because 10 squared is 100, right? So it's the inverse of exponentiation. So, okay. So you can prove the following property. So if you get 10 to the x minus 2y plus y, then you can say that a is so x is log of a, y is log b. So from this you can piece together, you get the property that the logarithm of a plus the logarithm b is the logarithm of a times b. Okay? Because here a is 10 to the x, b is 10 to the y. So the logarithm of a is x, the logarithm of b is y. So this is x plus y over here. And a times b is 10 to the x plus y. And the log of 10 to the x plus y is just x plus y. So the statement is true. Okay? So why is this useful? So the log function turns multiplication into addition. So here you're given that f is a continuous function. Why would I do that when we've just covered Cauchy functions for real numbers with those conditions over there?
Because then f of cx is equal to cf of.
Okay, so one of the conditions of the Cauchy function for real values was that if f is continuous, then f of x equals cx is a solution. Okay. But in this case, f of x equals cx is not a solution, so that doesn't seem all that useful. But the difference between the Cauchy function and this function is that there's a plus, where here there's a multiplication. Okay, so you've just learned that the log function turns multiplication into addition. So you may think of trying just try and take the logarithm of both sides. So by the question statement, we have that f of x plus y equals f of x times f of y, which means if you take the logarithm of the left-hand side, it will be equal to the logarithm of the right-hand side. So log of f of x plus y is equal to the log of f of x times f of y. Okay? And here you can separate the terms. Yet this is the logarithm of f of x plus the logarithm of f of y. Okay? So now this is very similar to the Cauchy function. We have some function, log of f of x plus y, is equal to some function of x plus some function of y. And so it turns out that log of f is continuous if f is continuous, which means that because it's a Cauchy function, log of f of x is equal to c of x for all values of x, where c is some number. Okay, and well, we don't want log of f of x, we just want f of x. So just how logarithms are the inverse of exponentiation, exponentiation is the inverse of the logarithm. So you can raise or do 10 to the power of the left-hand side is equal to 10 to the power of the right-hand side, which gives you that f of x is equal to 10 to the cx for all x where c is some constant. And from here you can check that those ones do actually satisfy the original equation for any value of c. And I won't go over it now, but it turns out that you can write this as just being some value, I don't know, b to the power of x, where b is some value that's related to c, but we won't go over that now. Okay, so that's an example of how you could apply the Cauchy function. Cool. So, next up, to finish off, I think we'll try this question, number 2. First step. Any ideas?
So we could substitute in a...
Before that, what's the first step of functional equations? There we go. Does f of a equals to a work? No. So you get 2a plus 2b has to be a plus b, which isn't true for all values of a and b. Does f of a equal a squared work? It's a bit more work, but it turns out it doesn't. So you notice that, okay, well, first off, f of a equals 0 works. So that's one possible solution. Also, f of a is 2a works. On the left you have 4a plus 4b, and here you would get 4a plus 4b, the same thing, so it works. Question? Okay. So now we can start plugging stuff in. Any ideas for what to try first? Okay.
A equals 0, A equals 0 first, and then you can just let B equal some variable, and then you can...
Okay, that's quite a lot of looking ahead, and we don't even know what A equals 0 gives us. So let's try that first. So first, just let A equals 0, I guess. Sure, we can say B equals 0 as well. That would be the natural first choice. So the left-hand side becomes f of 0 plus 2f of 0. This must be equal to f of 0. So 3f of 0 is f of 0. Okay, that doesn't seem all that useful. Okay. Next, let's try just letting one of them be 0, see what that gives. One thing to notice here is that we've got the 2 inside the function over here, but the 2 is outside the function over there. So that says that you can't just decide arbitrarily let this one be 0 and keep going as is, because it makes a difference which way around you choose it. So let's first say let a equals 0 and b equals k, I guess, where k is an integer. So that you're right. So a equals 0 and b equals k. What does that give us? Yeah. Yep, cool. Okay. That still doesn't look all that useful by itself, but maybe it is. Now we try the other one. So if a equals k and b equals 0, well, you get f of 2a plus 2f of 0 is f of k over there. Okay. Again, that doesn't seem super useful. Yes?
Equate the two, because they are both equal together.
So you notice that you have an f of k over here and an f of k over here. So since this is equal to f of k and this is equal to f of k, those two things must be the same thing. Okay, but before we just blindly jump into it, see if that will be useful. So here we have the function applied to itself, which is not nice, so we'd like to get rid of that. And here we only have the function being used once, and there's that extra 2 over there, but we'll deal with that later. So maybe it works out to be nice. So we get that f of 0 plus 2 f of k is equal to f of 2k plus 2 f of 0. Okay? So here you can rearrange this slightly. You can get rid of that, move it over there. So we get 2 times f of k is f of 2k plus f of 0 for every value of k that you choose. So that is useful, because if you have f of 1 and you have f of 0, you have a way of getting f of 2. And if you have f of 2, you can get f of 4, and then you can get f of 8, and then f of 16, and maybe you get an answer from there. Okay? Any ideas what to try next? Any suggestions? Okay. So, let's see. Well, we have 2a over there, we have b over there, and we have a plus b over there. So what happens if we say let if you say let a equals to 0 and b is x plus y, where x and y are 2 integers. Okay, so you get f of 0 plus 2 f of x plus y is equal to f of 0 plus x plus y, which is x plus y. Okay, but we know that this is equal to f of 2x plus 2 f of y. Right? If you let x equals, a equals x and b equals y, you're to get that out. Okay? Here, we have 2 inside of the bracket again. So that's not very nice. We don't want just for even numbers, we want for all possible integers, x and y. But we remember the previous step that we did, where we got f of k is f of 2k plus f of 0 for whatever value of k you choose. In particular, let's see what happens when we let k equals to x. So from this, we have that 2 f of x is equal to f of 2x plus f of 0. Okay, so this seems slightly better. We have just f of x over here and f of 0 and this term here. So we can get f of 2x in terms of f of x. So, and now we try plugging this into this and see what we get. So if you take these two statements together, you get f of 0 plus 2 f of x plus y is equal to 2 f of x minus f of 0 plus f of plus 2 f of y. Okay. Now we can move this over to this side, and we end up with 2f of 0 plus 2f of x plus y is 2f of x plus 2f of y. So there's a whole lot of 2's there that we can get rid of. We get f of 0 plus f of x plus y is f of x plus f of y. Does that look suspiciously familiar to anyone?
Almost a Cauchy.
Yep. So if you look at the Cauchy function, it says if f is a function from z to z, and f of x plus y equals f of x plus f of y, then f of x is c times x is the solution. Okay, so in this case we still have that f is a function from z to z, but we almost have that exact condition. It's just this pesky c0 over there. So if we knew that f of 0 was 0, we would be done, but we don't know that. So we have to come up with another plan. Any ideas on how to fix that? Okay. Well, what do we have? We have a function that we don't know the value of f of 0 for. So this sometimes comes up with questions where it would be very nice if you knew one specific value. And it would be extremely nice if f of 0 was equal to 0. So maybe we can manipulate this expression slightly to end up with something that's still equivalent to this statement, but it's a lot nicer to work with. So we create a new function, g being from z to z, that is defined by let g of n equal f of n minus f of 0. Okay, so we can take this statement over here and write this up. So you get that f of n is g of n plus f of 0. So we can take this definition and plug it into that expression we found, and we get, if you leave f of 0 as it is, plus f of x plus y, which by this definition is g of x plus y plus f of 0. And on that side we get g of x plus f of 0 plus g of y plus f of 0. And now we simplify all of the f of 0s, and we get that g of x plus y is equal to g of x plus g of y. And that looks really nice, because that's exactly what we're in the same form as the Cauchy function. Okay, so using that, we know that g of x must be c times x, where c is some constant. Okay, and that means that f of x must be c of x plus f of 0. So now we have something of that form. C of x, or f of x, is c times x plus f of 0. Now this is an explicit form for the function. So we have f of x something times x plus some constant, whatever it is. So at this point we've shown that all possible solutions to the original question must be of that form. So maybe all possible functions of that form work. The only way to know is to check. So if you check, the left-hand side is f of 2a plus 2b, which is 2ca plus 2cb plus 3 times f of 0. I think that's right. Okay. You just put it into the equation that I've given there. And right hand side is f. Okay, and this is c squared a plus c squared b plus c plus 1 times f of 0. Okay, well, those two things don't look the same at all. So we see when they are actually the same thing. Okay, so we get 2 times a plus 2b plus 3 f of 0 has to be equal to c squared a plus c squared b plus c plus 1 times f of 0. That's scary. Okay. So we can try and factorize that a bit. To the side. Get a times c squared minus 2c. B times c squared minus 2c is equal to 2 minus c times 0, I believe. Okay. So you can factorize that top part to get that a plus b times c squared minus 2c must be equal to 2 minus c times f of 0. Now, notice that this is constant, 2 is constant, c is constant, and f of 0 is a constant. But this is a plus b times some constant. So if you have something that changes times a constant is equal to a constant, then those constants must be 0. So the only case where this is true is if c squared minus 2c is equal to 0, which you can factorize to get c times c minus 2 is equal to 0, so c equals 0 or c equals 2. And from there you get that f of x must be 0x plus f of 0, or f of x must be 2x plus f of 0. And if you check those, the f of 0s should come out to be 0 as well, which means the only solutions that you should get are f of x equals 0 and f of x is 2x for all x. Actually, I think adding constants works. No. Okay, and you can check those and they will work, and that's the end of the question. Okay, so as was correctly pointed out at the start, this was an IMO question from this year. First question. So the point of this was that even at the highest levels of questions for functional equations, you still just plug in stuff, see what you get, play around with it a bit, see what you get, and manipulate all of these expressions until you get something nice, and then maybe you can use some theory to finish it off. Okay, and fun fact, this question was set by Liam. Yeah. Cool. So I think that's all for today.